In this video, we're going to be talking about oscillations. So we're going to start off with simple oscillations and review those in a little bit of mathematical detail so that we can use those techniques to move on and study damped oscillations. So simple oscillations, the force depends on the distance that the mass has moved. So this is our standard force is equal to minus kx equation, where k is the spring constant. And this is a second order differential equation. Um, and that means that we have two solutions and we need to have either two boundary conditions or two initial conditions to completely specify the trajectory. So let's start off with this equation. So x double dot is equal to ax. We can write down the solution to that. So we've got two solutions. So e to the square root at and e to the minus square root at. But we don't know the relative weightings of them. So we're going to give them each some arbitrary constant. So these are our a's and b's. In this case, our a is going to depend on the constants of our equation. So it's minus the square root of k over m. And since this is a minus, when we take the square root of it, root a is going to be equal to I times omega. So our full equation looks like this. So a e to the I omega t plus b e to the minus I omega t. Um, and we'd like to get this into our standard sines and cosines um, format. So we can do that using Euler's equations. And so Euler's equations are a way to look at the complex plane. So imagine I have my complex plane here. I've got real numbers here and imaginary numbers here. And so what this is saying is that e to the I alpha is basically specifying an angle on the unit circle. So here's my unit circle, and here's some angle. So what this is saying is that my point here is going to have some real component, so it's cosine of that angle, and some imaginary component, so sine of that angle. And so I can now apply Euler's equations to this solution because we do know that our trajectory x is purely real. So I can split this up. So I have a times cosine omega t plus sine I sine omega t, and b times cosine of minus omega t plus I sine of minus omega t. And then I can group terms. So I can group real terms and I can group imaginary terms. So I end up with my terms acting on my cosine. So I've got a plus b times cosine. So a plus b has to be real, purely real. And the sine term, which comes along with an I, so this is our imaginary part, so this is a minus b. So a minus b has to be purely imaginary. So that means a and b are complex conjugates of one another. So I can rewrite this in a number of different ways. I can rewrite this assuming that my A's and B's give me the right real and imaginary components. So I have now the standard C cosine omega t plus D sine omega t term. Or I can think of this going back to this complex this complex plane notation. I can think of it as cosine plus some phase shift. So these are all different ways of writing down my simple oscillator. And we're going to be using different versions of this all throughout the semester. So for damped oscillations, let's imagine that the particle at the end of the spring is also undergoing drag. So our equation of motion is now going to be given by force is equal to minus kx minus bx dot. So I'm going to rearrange the terms just a little bit and write it like this. So this kind of feels reminiscent of like a quadratic equation or something like that. And to make our lives a little bit easier, I'm going to simplify these terms with some notation. So this b over m, I'm going to call 2 beta, and k over m, we're going to call omega naught squared. So root k over m is the frequency of the oscillation in the absence of drag. So that means that I can rewrite the equation as x double dot plus 2 beta x dot plus omega naught squared x is equal to 0. So there's a change of variables that lets us rewrite this equation as u double dot is equal to au. And we know that that type of equation has solutions of the form x is equal to something e to the rt, where we don't know what r is right now. So instead of doing all of the algebra, what we're going to do is we're going to take this solution as an ansatz and guess it and see what this tells us about r. So let's guess x is equal to e to the rt and see where that takes us. So our equation now looks like, so we've got r squared e to the rt plus 2 beta r e to the rt plus omega naught squared e to the rt is equal to 0. So nicely, all of the e to the rt's drop out, and we're left with a quadratic equation for r. So we've got r squared plus 2 beta r plus omega naught squared is equal to 0. So we have solutions for r that are r is equal to plus or minus square root beta squared minus omega naught squared minus beta. So that gives us our full trajectory. So x as a function of t is equal to a times e to the minus beta plus square root beta squared minus omega naught squared plus b times e to the, all of this is times t, e to the minus beta plus, sorry, minus the square root of beta squared minus omega naught squared times t. So that's our full solution. And now we can imagine studying what happens under different sets of parameters, particularly what happens when beta is bigger or smaller than omega naught. So this is our equation. Again, here I've pulled out the e to the minus beta. So this is just a purely decaying term. So if I have now beta is less than omega naught, so that tells me that this term is negative. So everything inside the square roots is negative, which gives me imaginary solutions. So this tells me that the square root of beta squared minus omega naught squared is less than 0. So my solution now is something that's purely decaying, so I've got this e to the minus beta t term times something that's oscillatory. And so that gives me something that is oscillatory, but the peaks decay. And they decay according to e to the minus beta t. If beta naught, or sorry, if beta is greater than omega naught, then all of the terms in here are positive, which means that I end up with two kinds of decay. So I basically end up with A times something that's decaying with one rate. Um, so let's imagine it decays really fast. Um, and then I'm going to add to that B times something else. Let's imagine it decays a little bit slowly. So I can end up with two different types of solutions depending on what A and B are. So I can end up with something that's either purely decaying, so one way or the other, um, or I can end up with something that goes like this. When omega naught is zero, we have sort of a special case. So that tells us that we really have only one solution. So x of t is equal to e to the minus beta t. But we know we have to have two solutions and two linearly independent solutions at that. So we have another solution now. So let's multiply this by some prefactor a. So we have to add to it t times e to the minus beta t. And let's multiply that by some constant b. So this gives us our solution. And for this one, we have something that is uh, exponentially decaying. So we end up with, so let's pull out a e to the minus beta t times 1 plus some constant times t. And if you look at the sort of rates of decay, we know that exponential decay is always going to win out over linear growth. So at long times, this is again going to decay exponentially.